So we got an elevator here that is moving at 15 meters per second and then slows down to 0 meters per second at a constant acceleration. So we're asked what is the apparent weight of the person inside it as the elevator slows down. So we got a kinematic equation here which we are going to use to calculate our acceleration. And this simply works by doing A equals minus v0 squared divided by 2d, because our final velocity is 0, and by calculating this we get an acceleration of minus 2.25 meters per second squared. Then we need to see how the weight changes, and in order to do this we need to know what the weight would be like if we were comparing the rest scenario. So the rest scenario shows us that the normal force equals mg, right? So in our non-rest scenario we got that the normal minus the weight equals ma. So by substituting mg and comparing these two equations, we get that mg plus ma divided by mg equals our apparent weight, our change in the normal, which is what we wanted. So if we do this, if we divide these two equations, we cancel our masses and we get a value of 1.229, which divided by 1 will give us the percentage, and doing this times 100 we get a change in the mass of about 123%. So we got a box here that is being pushed with a work of 6,300 joules up an inclined plane of 6 meters and 3 meters tall. Alright, so what we are asked is what is the force that friction is exerting on the box. So to do this we can use the work theorem, which says that the total work equals the sum of all the work forces. So which work forces can we find here? We got the box's weight over here, which needs to be pushed 3 meters upwards. We got the friction force going in this direction, and we got our force, our work going in this direction. So we can substitute them here. 6,300 joules, which is going positive direction, minus 900 times 3, which is going in the negative direction downwards, and minus fk6, which is the distance that the friction moves. So when we work the friction out of here, we got that fk equals 6,300 minus 2,700 divided by 6, which equals 600 newtons of the friction force. That's it. So we got a particle over here that is moving horizontally parallel to our x-axis, and we know that it moves a distance of x equals 0.5 meters with a force of 260 newtons during this distance. So we know that work is an integral because we have to calculate a certain region, a certain area, and this equals force times distance differential element of this integral, which we can already substitute over here, 260 newtons times x dx, alright? So we know that it moves from 0 to 0.5, and when we do our integral, we get over here that we got 260, which is a constant force, times x squared divided by 2 from 0 to 0.5, and when putting this in our calculator we get a work of approximately 33 joules. That's it. So we are asked at one question, the momentum in a system is the same at two different points in time, when? And we have several options, but we know that if there are no external forces, then that means that the change in the momentum is 0, because as Newton wrote, the summatory of the forces equals the change in the momentum. And if the sum of all our forces equals 0, then that means that the change in our momentum is 0, and therefore our momentum is a constant. So in the next question, we are asked, there is one mass of a mass m and one mass of a mass 2m. Both are pushed with the same force during the same time. What is the difference between their impulses? So we got that our impulse equals force times the change in time equals the change in the momentum. But if both masses have are pushed with the same force during the same time, which is work, then that means they have the same impulse. So impulse 1 equals impulse